All right, so getting back into the lecture, we're jumping into section 5.4. And section 5.4 asks a question about the area between two functions. So let's think about this for just a second. Once I get this erased, I should have done that over break. Oh well. So we've got two different functions. Let's say one does like that, and the other one does like this. And let's say that what we want is the area in here. So that's going to be the area that looks something like this. Right? Everyone at home, can you see this?
No.
No? All right. We draw it again then.
Yeah, that's a lot better.
Awesome. So the area we're looking for is going to be this area inside of here. It looks something like that. How the hell are we going to do that? Well, let's start by deconstructing this problem. Let's start by saying, I know how to get this area. Right? And I know how to get this area. And if we look at what we're drawing, we got this, we got this going on. If we look at what we're drawing, the way this works out is this area here, that's this stuff right here, right? And this area here, well, that's this stuff right here. And what's left over, when we remove that intersection of the two areas, is the area we're looking for, right? So, to find the area between these two functions, we can start by saying, of these two functions, which one's the largest one? Let's find the area under that thing first. Then, subtract from that answer the area under the smallest one. And that's how we're going to find the area between two functions. Just like we did here. This area corresponds to this bit. This area corresponds to the big bit. And the area in between, right through here, is the area that remains when we remove the little bit from the big bit. Does that make sense to everyone? Let me pose this question in a slightly different way. The idea of what we're doing is the same as saying, I want if I can draw this well, I want the area of everything in black. Well, the way I can find it is by starting with the area of the square outside and subtracting from that answer the area of the circle inside. In the same way we can do that here to find the area of the black bit, the stuff that remains. We're going to do that here to find the area between two functions. It's the exact same idea. So, like I said, we want the area between these two functions. We can start by saying, hey, I know how to get this area here. That's pretty straightforward. And I know how to get this area here. That's pretty straightforward. So if I remove this bit from this bit, what I'm left with is going to be this, right? And that's it. So to find the area between two functions, we're going to take the integration from a to b of your larger function minus your smaller function integrated with respect to x. And we can break that up accordingly too. So the area between two functions is the integration from a to b of your larger function minus your smaller function with respect to x. That's it. The end. That's all she wrote. So question happens, what if these two functions intersect each other? So what if it does one of those crisscrossy things that we've seen a couple of times in this class, like if it does something like that, and you want this area here. Well, you would just break your interval up. You say, all right, up to this c value, f of x in red is greater than g of x in blue. And after it, g of x is greater than f of x. So you would just flip those, right? You'd say integrate f of x minus gx from 0 to c plus the integral of gx minus f of x from c to b. Does that make sense to everybody?
Yeah.
Awesome. So, giving a quick example, we've got two functions, x squared plus 2 and y equal to x. These two right here. So we've got this really weird rhombusy looking doodad of a thing. I don't even know how to describe that shape. Diamond-esque. But we know that it's bounded by x squared plus 2 from above, and it's bounded from below by just x. And across, it's bounded between x equal to 0 and x equal to 1. So we can integrate this thing to find the area, right? You say first, take your function x squared plus 2 and subtract from it x. Then integrate from 0 to 1. And looking at it, x squared plus 2 is our larger function. So we're going to take f of x to be x squared plus 2 and g of x to be x. We're going to subtract g of x from f of x. We're going to integrate from a to b. Well, a to b is 0 to 1. So we get this here. This is f of x, this is g of x. Everything's looking good so far. So we rearrange our terms now because, well, hell, we can just drop the parentheses, rearrange those things, and integrate it. It's just a polynomial. That's straightforward to integrate. Nothing crazy here. Once we integrate it, we apply our bounds, and we get our solution. Check it out. Since we're evaluating at 0, those all disappear, right? Since we're evaluating at 1, well, 1/3 minus 1/2 plus 2. It's going to come out to be 11/6. And that's because that's the shared factor between 3 and 2, right? That's all this is. There's not a whole lot to this. It's rinse and repeat from exactly what we just talked about, but now we're applying it to get the area between two functions. And it makes logical sense, right? We're just removing the thing that would represent the area under both of them to get the area in between the two of them. All right, now what about something like this? This is x squared, or 2 minus x squared and x. First and foremost, what does this function look like? Well, this function excuse me, 2 minus x squared looks about like that, right? With this being the point, 0, 2, this being the point, square root of 2, 0, and this being the point, negative square root of 2, 0. Okay. Now, this is why we said we're going to go with plotting the other function, and it's going to look something like this. Agreed? We want the area bounded between the two graphs. So we want the area between the two graphs. If we extend this out further, we find we get an intersection down here, right? And the area bounded between the two graphs, that's all of this stuff. So now we need to find what our missing points are. We need to find these two intersection points, x1, y1, and we need to find these. Why do we need to find these? What do y'all think? Why do we need to find those 2 points? It's because what we're really looking for is just the x value. That way we can have our bounds. This is x1 here. This is x2 here. So when we go to integrate this stuff to find that area, this thing, it's going to look like, once I get this erased again, that area, which I'm going to write as A, is going to come out to be the integral from x1 to x2, those intersection points, because those are the 2 points that define the bounds, right? Of the larger function is going to be 2 minus x squared The smaller function is going to be x. We're integrating all of this with respect to x. Okay. What the hell is x1 and what the hell is x2? Let's stop and think about what those 2 points represent. At x1, our 2 functions are equal, right? And at x2, our 2 functions are equal. Those are the only 2 points that ever happens that those 2 functions are equal, right? So we can find them by solving the problem 2 minus x squared is equal to x. Agreed? Well, to solve this, that's equivalent to solving 0 is equal to, we're going to subtract everything on the left from everything on the right, x squared plus x minus 2. Well, this thing, that factors really nicely. It factors to x plus 2 times x minus 1. So when this is equal to 0, well, when our 2 things are set equal, that means this function is equal to 0, right? When this is equal to 0, one of these 2 factors have to be equal to 0. When this is equal to 0, we get x is equal to negative 2. And when this is equal to 0, we get x is equal to 1. So we just found that x1 is equal to negative 2. We don't necessarily care what y1 is. And x2, well, it's equal to 1. Whatever y2 is. So now we can plug those values into our integral. We can say, cool, this is the integral from negative 2 to 1 of 2 minus x squared minus x integrated with respect to x. Well, I like to write everything in order of degrees. So this is negative x squared minus x plus 2. Same thing, right? When we integrate this thing out, we're going to get, this is going to come out to be negative x to the third over 3 minus, this is going to give us the second term, it's going to give us negative x squared over 2. And this final term is just going to give us 2x. We're integrating between negative 2 to 1, so we need to put our bounds back in. And from here, it's just plug and chug. Nothing new or exciting from this point on. So let's jump to the solution. Looking at what they've got, it's the exact same graph, right? Exact same. You got your upside down parabola, you got your line y equal to x. Something that might be convenient to notice, from negative 1 to 1, well, let me step back. The function x is odd, right? And the function 2 minus x squared is even. So from negative 1 to 1, x is going to be 0, right? That integral is. And 2 minus x squared, well, that's just going to be 2 times the integral from 0 to 1, right? So that might be something useful to notice here. Might be. It is, honestly, but it also could add to your work. It just allows you to rearrange things in a nicer way. But looking at the solution altogether, look at what they've done. They start by saying, all right, obviously f of x is going to be 2 minus x squared because that's the bigger function all the way through. So obviously then g of x is going to be x. All right. Well, what about your bounds? We got to solve the case where our two functions are equal. So we're going to equate the two functions and solve for x. We're going to plug it all together, rearrange everything as we please, integrate it, remember to carry your bounds over, and adjust and do the calculation from there, the arithmetic. Notice what they've got is exactly the same. So some of these problems do take a little bit more finagling. For example, this one. We want the region of this parabola bounded by the x-axis. We want the area bounded there. So what is that going to look like? Well, we can start by observing that this function, factor it out. Factor it out pretty nicely, actually. And start by saying, cool, we've got x squared minus 3x minus 4. That factors pretty easily into x plus 1 times x minus 4. Okay. Well, because the leading term, x squared here, is positive, we know that our parabola is going to be a bowl shape, right? It's going to be facing up. And we know that when x is equal to -1, our parabola is going to pass the y-axis, the x-axis. And when x is equal to 4, we're going to pass the x-axis. So it's going to look something like this. Yeah? This is the point -1, 0. This is the point 4, 0. Now, the area bounded by our graph and the x-axis, that's just this stuff right here. So all we're going to do here, we're going to integrate from -1 to 4 the function x squared minus 3x minus 4 integrated with respect to x. Because all that integral is going to do is tell you the area between our function and the x-axis, right? So anytime you do this, you take the integral of a function f of x dx. This will always compute the area between your function and the x-axis from x equal to a to x equal to b. Well, coming back over here, we've got x equal to -1, x equal to 4, and this thing is going to compute the area between our function and the x-axis. Well, that's going to be what we have in red. That's it. From here, we're just going to integrate and then apply those bounds accordingly. So this thing is going to come out. We're going to say, cool. This integral is 1/3 x to the third for this first term minus 3 over 2 x squared for that second term minus 4x that third term. Now we're just going to apply our bounds. and calculate. So looking at the area that we want to find, it's that area in blue. Now, they do something a little bit different here. They go ahead and factor everything out like I was talking about. But they argue that you have one function that's a constant, f of x equal to 0, and another function that is our function in question. So when we set this up, obviously 0 is larger than our function x squared minus 3x minus 4. That we've already seen. So since f of x is larger than this, we're going to say 0 minus that thing. Notice I have a boo-boo in my work, don't I? Why is that? Say what?
Is it because f of x equals 0?
It's because of what this calculates. This calculates the area, but it's the signed area. What we're trying to get is just the area. So my answer is the negative of the correct answer. And that's because my answer is the signed area. Everything, all area below the x-axis is going to be negative when you integrate it out straight, right? When you just apply the definite integral as it is. But what they're asking for isn't the signed area, it's the proper area. And that is going to be the negative of our signed area. Or, as they wrote it, 0 minus our function, integrated from -1 to 4. Does that make sense to everyone? People at home, does that make sense?
Yeah.
Cool. Cool. So once you do the arithmetic, you're going to get 125 over 6 square units. That's the entire area underneath or in between the x-axis and our function. Now, in the case of area bounded between these two functions, we do, again, pretty much the same thing, except here, we have to break it up like I was talking about before. The area bounded between the function -x squared plus 2x and the function 3x cubed minus x squared minus 10x, well, that's all of this stuff, right? But for part of it, one function is above the other function. And for the other part, that flips. So we're going to have to break up our integral from their first intersection to their second intersection, from their second intersection to their third intersection. Does that make sense what I mean? So the way to go about this is we set our two functions equal to each other to find, to blah, 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 I can't talk now, to figure out what these intersecting points are. We say, cool, what happens between these two first intersections? Which function's above, which function's below? Cool, what happens between these two intersections? Which function's above, which function's below? And we break our integral up according to that. So from -2 to 0, we have f of x is larger than g of x. And from 0 to 2, we have that g of x is larger than f of x. We put all of this together and integrate, and we get our answer. Make sense? People at home, y'all are killing me. Are we here today?
I'm the only one who ever answers, so I'm tired of answering.
That's fair. Trying to figure out, I want to include this particular consumer surplus and producer surplus stuff. No, I don't. All right, so now we're jumping ahead to section 5.6 because section 5.6 I think is perhaps the most important section in all of chapter 5. Why are you not letting me see that? What slide are we on? Come back. There we go. Always show slide bar. 66 out of 90. All right. Yeah, I'm jumping to this now. All right. Jumping to section 5.6. What we're going to talk about is what this definite integral actually is, where it comes from, why it is what it is. Now, before we get into the nitty-gritty of all of this, like I say here in the notes, I'm going to jump outside the scope of the class for just a minute because I think the notation will help us. So the notation we're going to use is this funny looking E with an upper bound and a lower bound, and something that looks like a function, right? And what this is telling us is you're going to do your function on each individual step value from A to B. Now, what does that mean? What do I mean by that? Let me show you. What I mean is that in the case that you're just adding up i's, and you want to add up from 0 to 5, what this notation says is, all right, plug in 0, then plug in 1, then plug in 2, then plug in 3, then plug in 4, 5, so forth, so on, and add all of those up from your lower bound to your upper bound. Now let's say we change this. Instead of it just being the function x, which is what this would represent, let's imagine it's x squared. Now we're going to say, all right, plug in 2 squared, add 3 squared, add 4 squared, add 5 squared, so forth, so on. So we're just applying the rules right here to each step value between your lower bound and your upper bound. People at home, are we cool with that? Yeah? Dope.
Yeah.
So once we do that for each of those values, then we're going to add them all together. That's all this notation means. Iterative addition following a certain set of rules for step values between your lower bound and your upper bound. Now, how this is going to apply to the definite integral, it's going to be by approximating this area first. Let's say we want to approximate the area underneath this function f of x. Well, we could do it with two different sets of rectangles. Rectangles whose top left corner is equal to our function, or rectangles whose top right corner is equal to our function. This one is a weird case here. I don't know why it's doing that. It should be over, but mistakes happen, I guess. But then we're going to take and add the area of each of these rectangles together. And that's going to approximate the area underneath our curve. But it's going to have a little slop, either in the negative direction, like with these left rectangles here, or in the positive direction, like these right rectangles here. So this is going to underestimate, this is going to overestimate. Notice it's not necessarily true that if you choose left or right corner, that'll determine if you're overestimating or underestimating. It just happens to be the case here. So the point is to say that when you're using these rectangles to approximate the area, you're going to set one rule for how you're going to decide the height of your rectangle. You're going to follow that rule for every rectangle. Then you're going to say, okay, what's the area of each of those rectangles? Now add all those areas together, and depending upon the rule you chose and the function you're using or you're trying to evaluate, you're either going to overestimate or you're going to underestimate. Is everybody cool with that? People at home?
Yeah.
Yeah? All right. So what we just described is this thing called a Riemann sum. And a Riemann sum says, all right, take your x-axis between B or between A and B, and you're going to chop it up into little intervals. And then each of those intervals, or each of those sub-intervals inside of your interval from A to B. Excuse me, let me draw this on the board as I say it. Like that. No. All right. We've got our function, looks something like this. And we want this area. X equal to B, X equal to A. You want to approximate that area. So first, we've got the interval from A to B. Now we're going to chop it up into equal sub-intervals. What I mean to say is you're going to determine how you want to break this up. The easiest way to do that is to say, all right, I've got a delta x. That delta x, let me actually step back. I've got the entire length from B to A. The length is equal to B minus A. Now, I'm going to take and cut that length up into equal parts. How many parts do we want to cut this up? People at home, give me a number. How many times do we want to cut up the interval from A to B here? How many sub-intervals do we want to cut this up into?
2.
2? Okay. So we're going to cut it up into 2 sub-intervals. So we're going to go halfway in between. Where is this sub-interval? Let's call that x1. Where does that exist? Well, right smack dab in between the two, right? So x1 is going to be right in the middle of the 2. How are we going to do that? How are we going to represent that? We're going to say, first, what's the distance of each of these two intervals? Well, that's going to be B minus A divided by 2, because we broke it up into 2 sub-intervals. Then we're going to say, all right, then x1 is just going to be delta x plus A, right? So this x1 value is A plus delta x. And if we were to do it again, we would get to B, right? Let's say we broke it up into 4 parts. So we have x1 being the far left point still, other than A, right? So the point that comes after. So the end of our first sub-interval. x2 is the end of our second subinterval, x3 is the end of our third subinterval, and b is the end of our fourth subinterval. In this case, the length of each of these subintervals, well, that's just going to be b minus a divided by 4. And x1 is still going to be a plus delta x, but now x2 has been introduced. That's just going to be x1 plus delta x. Well, that's equal to a plus 2 delta x. x3 is going to be x2 plus delta x. Well, that's equal to a plus 3 delta x. And b is equal to x3 plus delta x, or a plus 4 delta x. Now, really quickly, let's notice what a is equal to. A is just a plus 0 delta x, right? Okay. So we've got each of these subintervals. We have a nice way of defining where all of our different parts are going to end up, right? Let's start by renaming a x0, because that's going to be convenient for us, and b x to the 4, or I mean x sub 4. That's just going to be convenient for us. We have a way now of finding each one of these based on their subscript. So if we were to take and cut this up into n many parts, however many parts you want, we would say that x0 is still equal to a plus 0x, x1 is still a plus delta x, but now we're dividing it into n many subintervals, as many as we want, and the rule for finding delta x is just going to be b minus a divided by n, and the rule for finding each one of these is going to be a plus whichever x value we're at, right? So we could say delta x is equal to b minus a divided by n, and x sub n is equal to a plus n times delta x. From here, we're going to come up with a rule for how we're going to choose the height of each of our rectangles. Let's say, cool. We're going to make a rectangle for each of these. We could choose to set a middle point in between each of our x values equal to the height of our function. Or we could choose the left corner, we could choose the right corner, the 1/3 in between, however you want to do it, whatever rule you want to use. Use it, stick with it, but it has to be repeatable for each of these, right? So here, let's say we want to use the left corner. Notice when we do that, the area we're going to get is just a little bit smaller than our actual area, right? You got a little bit of slop up here, a little bit of slop up there, a little bit of slop up there. It happens. We're just going to underestimate a little bit. But if we wanted to make our approximation better, we could choose to use smaller rectangles, right? Then the underestimation would be a little bit closer. It would be less than it is currently. But before we get there, we're going to take and find the area of each of these rectangles. So here, this area, y'all can't see that. And this is looking messy, so let me clean this up just a little bit. Keep that line. All right. So the area of our first rectangle, let's call this area 1, is going to be equal to delta x times our function, since we're choosing the left corner, our function evaluated at x0. Right? This next area for this rectangle, the second rectangle, it's going to be delta x times f evaluated. Well, the left corner here corresponds with x1, our function evaluated at x1. The third rectangle is going to be delta x times the function evaluated at, well, the height of our function is f of x2. And the height of our final rectangle is going to be delta x times f at x3. So the entire area of this, let's call it capital A, is equal to delta x times f at x0 plus delta x times f at x1 plus delta x times f at x2 plus delta x times f at x3. We can abbreviate that using the notation we just said. And now you see why I wanted to use that notation, because this just sucked to write. Instead, we could say, cool, this is equal to the sum of delta x times f evaluated at xn, where n is between 0 and 3. This is why I introduced that notation. This stuff, great. It reduces what we've got to write by a lot. But this gives us the approximate area. Now, notice what happens. I should actually choose k instead of n. Since I use n as the number of subintervals here, let me use k here. Now notice what happens when we let that area, the number of rectangles increase. And I don't think I have the visual on, I don't. Notice what happens when we let the number of rectangles increase. We'll get a better and better approximation. You can't see it in this because unfortunately the GIF doesn't work. But I do know where I can grab it. Give me just a second here, everybody. Let's go back to Blackboard. Courses. Course material, I think it works out of the PowerPoint. Let's stop share, open up the PowerPoint really quick. Open up the PowerPoint. PowerPoint open. There we go. All right. Go back to Zoom. I'm going to scroll all the way down. Notice what happens when, like I said, we let the number of rectangles get larger. We get a better and better approximation over time. And that's what we're going to do here. We're going to send the number of rectangles we use to approximate this to infinity. Having just said that, what does that sound like we're about to use? Well, we're going to send something to infinity. We can't actually calculate stuff at infinity, but we could use the limit and see what happens as we get closer to infinity. And that is exactly what we're about to do. We're going to say, let the limit of those small delta x's go to 0. Then the width of each of our rectangles, that's going to go to 0. Which means as that goes to 0, you're going to have more and more and more and more rectangles. And if you could have something of 0 width, it's not actually 0 width, it's the infinitesimal width. But if you could have that, then you'd have to have an infinite number of rectangles to represent the area under our curve given our conditions, right? Does that make sense to everyone? People
Yeah.
at home, that makes sense?
Yeah.
Cool. So one way we could think of this is as delta x going to 0 or as the number of necessary rectangles, k, going to 0, going to infinity. Because k here is the number of rectangles we have, right? Because this is the area of each individual rectangle. So we could say delta x goes to 0, or since delta x is equal to b minus a divided by k, we could say k go to 0. I mean, k go to infinity. But again, x sub n, I write it as star x sub n. It could be whatever you want. And depending upon the rules, you're going to get different values for different types of functions. But what this is ultimately telling us is that you could take and use these rectangles to approximate any integral, which is great because there are some functions that we can't actually calculate the integral of. For example, something that is similar, not the same, but similar to what you've seen in class, without using a trick, we cannot evaluate that. It takes a trick to evaluate e to the negative x squared as an integral. So if we want to find a particular area from A to B here, we're going to have to use approximation methods. And that's what this is here. This is an approximation method that we're talking about right now. And it's used all over the place in mathematics. In fact, in aerospace and fluid dynamics, most of your, I shouldn't say most. Yeah, most, I should say most. Most of your problems can't be solved directly. You have to use a numerical method to solve them. And this is an example of a numerical method where you say, I can calculate something that's kind of close, but it's not exact. And I have conditions that I can use to get it closer and closer and closer. And I can look at what happens as I change those conditions to see if there's a convergence, a value that all of those changes work towards. And in that way, I might be able to find out what the exact answer is, or I might just be happy with my approximation, say, I don't really care beyond this. Let's go home. So, jumping ahead into an example of how we're going to do this, we want to use 5 rectangles here to approximate the area bounded by the function negative x squared plus 5 between x equal to 0 and x equal to 2. Well, we can find the actual exact answer, right? That's pretty quick and easy. You just apply the definite integral. We just got done talking about that. But to find, the approximate area using 5 rectangles whose height is going to be determined by the middle value of each subinterval. That's going to take a little bit more work, but not much. What we're going to do, we're going to say, all right, break up each of our subintervals, or break up our interval into each of our subintervals. Because we're breaking it up into 5 rectangles, and we're going from 0 to 2, we're going to have 0 to 2 over 5, 2 over 5 to 4 over 5, so forth and so on, right? Because delta x is just going to be 2 minus 0 divided by 5. So your first value is going to be 0. 0 plus 2 minus 0 divided by 5, that's just 2 over 5, so forth and so on, right? Then we're going to say pick the middle point of each of these intervals. That's going to be the value you throw through your function. Now, take that middle point, throw it through your function, and multiply it by your delta x. Do that with the second interval, do that with the third interval, fourth and fifth, and add all of those up. Because this is the area of your first rectangle, this is the area of your second, third, fourth, and fifth rectangle, right? You add all of those up, that's going to give you the approximate area. It's going to give you the total area calculated by those rectangles, which is approximately equal to the area under your curve. And you go through and you say, all right, pull out 2 over 5. I can calculate all of those function values. I can put all that together, blah, 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 blah. Because nobody wants to hear me keep talking. We're all ready to go home. I get it. But we go through, we massage the algebra. Like I said, factor out that 2 over 5, add up all those functional values, multiply that 2 over 5 back in to get 920 over 125, or 7.36. This is approximately equal to the area under our curve, approximately. And the general guideline for using what is called the midpoint rule is going to be, all right, take your delta x to be b minus a. So your interval, the endpoints of your interval, and you're going to divide it by the number of subintervals. Then you're going to find the middle of each of those subintervals. Then you're going to say, all right, the integral of our function from a to b integrated with respect to x is approximately equal to delta x times the quantity times, I shouldn't say times quantity. You're going to get delta x times the sum of your function evaluated at each of those midpoints. So here we're saying x1 is equal to some number in between a and a plus delta x, right? It's the value directly in between that. So as another example, here we're going to use the midpoint rule in 10 rectangles to approximate the integral negative x squared plus 5 integrated with respect to x from 0 to 2. That's going to be approximately delta x times your function evaluated at each of your midpoints, right? Notice that comes out, the approximation comes out to be 7.34. The actual answer though is 22/3. Check out what also happens as you use more and more rectangles. Initially, you start off with an error of, what is that, 0.03 repeating, something like that? I guess 0.027 repeating. You get a little bit closer here, a little bit closer here, a little bit closer, a little bit closer, a little bit closer. But already, by 15 rectangles, you got 2 decimals of precision. And you don't get a whole lot closer fast, but you're still pretty close, right? So the point here is sometimes when the integration is ridiculously difficult to work with, we have approximation methods that we can use that are pretty decent actually. That's, like I said, accurate up to the first decimal for just 5 rectangles. It's a little bit closer for 10. You're accurate up to 2 decimals with just 15 rectangles. Okay, excuse me. Allergies. Now, as another example of the midpoint rule, we could integrate from 0 to 1 the function 1/x² + 1. We'd start off by defining what our interval is, that's 0 to 1, break it up into 5 subintervals. Then we pick the middle of each of those subintervals, plug those into our function, right? Add all of those functional evaluations up. So add up our function evaluated at each of those subintervals and then multiply that by delta x. That's going to give us a decent approximation here. Yeah. Now in this case, we get that the answer comes out to be approximately 0.786. The answer is actually 0.785. So with 5 rectangles, you're up to 2 decimal precision. That's good. That is really good actually for that little bit of work. You're only off by 0.001. That's insane. So because these take a long time to actually write out, as you saw on the board just explaining it, that's why I'm walking us through some of these examples instead of actually doing them on the board. When it comes to the exam and the homework, on the exam, I may only give you one of these, if I give you one at all. Not if. I will give you exactly one of these problems. And in your homework, you can expect maybe 3 or 4 of them. I'm not going to go crazy with these because these take forever. Having also said that just now, it reminds me, when it comes to the homework, if y'all haven't already started, go ahead and start as soon as possible because you are getting a second homework set. And it will also be due next Wednesday. So you've got homework set 1, homework set 2, get through them because you got 2 exams next week as well. You got some work, all right? I just want to let y'all know in advance. But getting back to this problem, here we want to use the midpoint rule again. We want to set the number of rectangles equal to 10. And we want to do that to approximate this particular integral. So we're going to say, all right, delta x is going to be 1 and 3, right? Or well, I shouldn't say it that way. Delta x is going to be 3 minus 1, that quantity divided by 10. Agreed? So it's going to be 2 divided by 10, or just 0.2, right? 1/5, whichever way you want to write it. That's delta x here. Then you're going to have to say, what's in between each of my subintervals, right? What's the middle point in each subinterval? plug those values into my function, add the results together, then multiply by delta x. So you've got each of your subintervals broken up here, and then you have your midpoint for each subinterval. That's what's represented down here. Then you're going to say, take each of these, plug them into our function. Take each of those solutions, add them together. Then multiply by delta x. So the midpoints of each subinterval, again, we're going to take these, plug them into our function. That's what's inside the square brackets. Add all of those results together. That's everything you see inside the square brackets here. Then multiply that result by 1/5, and you get your approximation. Check it out with 10 rectangles. You have approximately 0.001 precision. That's, again, pretty damn good. So what this is ultimately telling us, though, is that the definite integral is the limit of a sum. And in that same way, it's somehow telling us something about the integral too, right? Somehow these things are all related again. And in the same way that we have a limit definition for the derivative, we now have a limit definition for the definite integral. So since this approximation is true, when we take the number of rectangles out to be infinity, we get that our approximation becomes equivalent to the definite integral in the limit as the number of rectangles approaches infinity. Now, like I said, you can't do this. This you can't calculate directly. Please, 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 please try. If you get an answer, if you figure out how to solve this, let me know too. I'd like some monies. But because we can't solve this directly, we're going to use approximations. We're going to use those rectangles. We could, like this says, use 10, 20, 30, 40, however many rectangles you want to get the result as close as you want it to be. There's actually other tricks to getting the exact answer here, but I'm not going to go into that. I just want you all to think about these different techniques, these reasons for using these techniques, and what these techniques tell us about the math underlining everything else. Having said that, I have just hit the end of this section. So I'm going to open up to any questions y'all have before I let y'all go. Do y'all have any questions for me about what we talked about today?
I don't think so.
No? Does the idea of the midpoint rule make sense?
Yeah, and you said there's going to be a couple of them on our homework.
Yeah, I'm not going to give y'all very many of those because they can take forever. What I want y'all to focus on more than anything else is going to be the actual integration stuff that we started off with, right? The area idea, the fundamental theorem idea, the average idea, the area between two functions idea. There will be some of this, but this will not be the majority of it.
Okay.
You're probably going to have 2 to 3 problems of each little bit that we've talked about today. Right, so like I said, fundamental theorem, area under a curve, area between two curves, average, and then 3 of these. So minimum of 15 problems, expect more though, because these are good problems for practicing other things that we talked about in the last class. Any other questions? No? Well, in that case, I will let y'all go. I'll stick around if y'all do have any questions.